Welcome, Algebra, to our next video, and it is called Recursive and Explicit Formulas. So the explicit part, that should be familiar, but the recursive part, that's the new thing today. And the learning target is I can create recursive formulas and convert them to explicit formulas. We can actually go the other way too if we need to. If you see at the bottom, there's a definition of a recursive formula, but before that, the word recursive, and this will help you remember what the difference is later on, but it comes from the word occur. So when something occurs, it happens. When something recurs, it happens again. So a recursive sequence is something that happens again and again and again and again. And we see that in sequences. We've seen sequences before where the same thing keeps happening. But the way you write a recursive formula, you basically say the thing that keeps happening. So it says it is written to show how the sequence changes from one term to the next, and the initial term must be given. So the initial term is not embedded into the equation like it is with an explicit formula. An explicit formula is like the equation of a line, but a recursive formula says like what a younger kid would say, hey, that pattern keeps going up by 3 every time. That's the pattern, but you also have to say where it starts. So if it starts at 100 and then goes up 3 every time, you have to say the initial term is 100. All right, we're going to ease slowly into this concept. So we're going to start. It says Allison is considering the pattern of numbers 5, 8, 11, 14, 17. This is something we've seen before with explicit. It's asking what type of pattern do you see? Well, I think they want you to realize that 8 is just 5 plus 3, and that 11 is just 8 plus 3, and that 14 is just 11 plus 3. So what we're doing every time is we're taking the number before it and adding 3. That's the pattern. Take the number before, add 3. That's how you get the next one. If we remember what the explicit formula was, we said that there was a common difference here of 3, an initial value of 5. And we wrote out our explicit formula like this. And we filled in the things we knew. We knew that the first value, the initial value, was 5 plus common difference of 3, n minus 1. Did a little bit of algebra to get it cleaned up looking. And there you go. And that's the explicit formula. But the explicit formula doesn't tell you the pattern, doesn't have the pattern right in there. It kind of does if you understand what 3n meant. And it also doesn't tell you naturally what the starting position is. It doesn't tell you that 5 was the first term. You have to kind of figure that out by plugging in a 1. Alright, so we're going to see how it's different with a recursive sequence. And we get Allison's friend Maddie to help us do that. She said she saw the sequence and wrote the following. A of n plus 1 equals A of n plus 3. And then she has to add some things on. This is not the most important part right here. We sometimes don't even need to include that. But we say for n that's greater than or equal to 1. In other words, we don't want to plug in like negatives for n, because we want to start with the first term and move up from there. And they tell us what the initial term is. You have to say what the initial term is in order for us to get the sequence going. So here's the important part. What does A of n plus 1 mean? Well, it means the term right after A of n. So we're going to say A of n plus 1 is the term after A of n. So if A of n was 10 and the next term is 12, then A of n plus 1 is 12. I like to call it the next term. I call it the next term because it's the next one. Usually this is how we write it. We say to find, this is kind of how I narrate it in my head, to find the next term, I take the term right before that and add 3. That's what I say in my head when I read that sentence. It says, what do we call the 5th term? Well, we call the 5th term a of 5, just like before. And how would we find the 5th term in terms of the 4th term? Well, to find the 5th term, we would say the 4th term plus 3. Notice, if I said the 100th term, you don't plug that in, because I could plug in a of 100, but it relies on me knowing a of 99 plus 3. And that doesn't help me very much. So this is why explicit formulas are actually way better and more versatile, where recursive sequences or recursive formulas are a little better for just generating the sequence from the start. Alright, here we go. Another friend, Matthew, wrote the following. So he wrote it slightly different. He said a of n is equal to a of n minus 1. So let's just write what this means. A of n minus 1 is the term before a of n. So he's just saying the same thing. You still add 3, but he's saying to find the current one, you take the one before it. So in this case, this is the one before this one. Take the one before it and add 3. So it's saying the exact same thing, but this time he's saying that the initial, or the 0th, that's not even a word, the 0 value, it's not called, it's hard because initial value sometimes is 1, sometimes it's 0, but we're saying a of 0 equals 5. In that case, that's his first term. And n has to be greater or equal to 0. This stuff sounds really confusing, but you don't need to know it as well as you might think. So what they're saying is to find, will this generate the same sequence? So let's just start by saying his initial value. His initial value is 5. We'll say a of 0. To get the next one, or a of 1, we plug 1 in to n. So if you imagine, I'm going to do a different color here. I want to say a of 1 equals, so I'm going to plug 1 into this little n right here, and that's a of 0 plus 3. Well, normally that wouldn't help, but I know what a of 0 is. It's 5. So what really we're saying is, right above it, a equals 5 plus 3, and I get 8. Well, this pattern, once you get that set, you understand what's going to keep happening. Now I'm going to have to add 3 again. I'm going to get 11, and so on. And I do get the same pattern. So this is just another way of writing in a recursive sequence. Now, you don't have to go back and forth. You can just pick the one you like and always write it that way. I prefer this one here. I much prefer writing it like this. It makes a little more sense to me in my head, because this one, I read it as the next one. But you do have to understand this one also, because sometimes it's presented to you that way in a book or a problem or a Regents. Alright, let's see. We have another thing here. Consider a sequence given by the formula. So this time they're giving you the recursive sequence. A of n equals a of n minus 1. Again, the way I don't like it as much, but that's okay, we'll deal with it. Where the initial term is 12, and n is greater than or equal to 1. Alright, we're going to start by writing the first 5 terms of the sequence. And I almost always recommend you do this just to get a handle on what this is really saying. So they're telling us that the initial term is 12, so they did one of the 5 for us. They have to, or else we don't know where to start. And I want to find, that's by the way a of 1 they're telling us. Where normally you use little letters, you'd use lowercase a. We used uppercase A for the last one because it was for Allison. So I want to find a of 2. Well, if I look up here, if I want to know a of 2, what that equals, then I do a of 2 minus 1. So I'm plugging in 2 for both ends here and here. So that's a of 2 minus 1, which is a of 1 minus 5. Well, I have a of 1. I know that that's 12. So this is really saying a of 2 equals 12 minus 5, which is 7. And once you get rolling, you do not need to do that every time. You just know that from now on, I just keep taking away 5. So this is 2, then negative 3, and then negative 8. And there we go. There's the first 5 terms of the sequence. And I know a of 1, a of 2, a of 3, a of 4, and a of 5. Alright, B says write an explicit formula for the sequence. Alright, well, there was only 2 things we needed to do the explicit formula, aside from the actual equation. So we need to start with the equation. We say a of n equals a of 1 plus d n minus 1. So we have to get these numbers, this a of 1 and d out of the recursive sequence. A of n stays a of n. And then d is the common difference, which is right in the recursive formula. It's minus 5. And then n minus 1 you just leave. Oh, I totally skipped some, didn't I? I forgot the a1. Let me go back. So that's 12 plus negative 5 times n minus 1. There we go. Now we can distribute, and we get 12 minus 5n plus 5, which is 17. Actually, we'll do negative 5n plus 17. So there it is. There's my explicit formula. Okay, so in part C it says find a of 6 and a of 200 of the sequence. Well, the recursive sequence is going to help us with a of 6 a little better because we left off on a of 5. Excuse me, to get a of 6, all I have to do is just go one more minus 5. So negative 8 minus 5 equals negative 13. And I used the recursive to get that. I could have used the... Oh, I can't spell. I could have used the explicit formula if I wanted to, but I would have had to plug in 6, do a bunch of math, and it would have taken me a little bit longer. All I have to do is subtract 5 from negative 8. Now, if I want to use the recursive sequence again, I'm going to be subtracting 5 a whole lot of times from negative 13. So this is where the recursive sequence fails to be very useful, and the explicit formula is much better. So I'm going to say a of 200 equals negative 5 times 200 plus 17. And I zipped ahead so that you didn't have to watch me do all the math. So you get negative 983 is the 200th term, or a of 200. That's the end of these notes, but I do want to add one more thing, just informally. Get a blank page up here. And let's say I have this typical pattern of something doubling every time 2, not doubling, excuse me, multiplying by 2 every time. So 2 times, oh yeah, that is doubling, oh my gosh. 2, 4, 8, 16, I know what I'm talking about. 32, blah, blah, blah. So it's doubling every time. And that's a geometric sequence. So we haven't talked about recursive sequences when they're a geometric sequence. So that's what we're going to do. We're going to say the initial value is 2. And I start thinking, what did I do to the last one to get the next one? Well, I found 32 by taking 16 and multiplying by 2. I did the same thing for 16. I took the one before that and I multiplied by 2. So that's what I want to say. I want to say to find the next one, to find n plus 1, I take a of n, the one before it, and I add, excuse me, I don't add, I multiply by 2. And that's not the end of the equation, because I also have to say that the initial term is 2. I wrote it there, but it has to be a part of the written equation. So you could write this a little bit nicer. You can say a of n plus 1 equals 2a of n. It really doesn't matter. And the initial value is 2. So there is a geometric sequence turned into a recursive formula. Alright, that's where I'm going to end it. Make it a little shorter than normal. And have a wonderful, wonderful weekend.